Welcome to the video help with physics problems for Physics 1A. In this video, we'll be covering Homework Set 2 Part 2, the second half of Homework Set 2, which covers the topics work, energy and conservation of energy. In 1121, this covers questions 7 to 11 plus a past exam question. For 1131 students, this video will cover questions 9 to 16 and a past exam question. Okay, this is problem 7 for 1121 or 9 for 1131. In this question, we have a block being dragged along the floor. It's dragged by a force applied to a rope. This force adds magnitude 7.68 newtons and is applied at an angle of 15 degrees to the horizontal. The mass of the block is equal to 3.57 kilograms and it moves a distance 4.06 meters across the floor. Now, part A asks us to calculate the total work done on the block. Well, total work is equal to the change in energy of the block. So this energy can have two forms. It can be a potential energy, so if the block was being lifted up, it would gain gravitational potential energy. The block's moving along the floor, so it's not gaining any gravitational potential energy. The block could also gain kinetic energy if it was speeding up. However, we're told that the block moves with a constant speed, so the block is not speeding up and so it's not gaining kinetic energy. So the block is in fact not gaining any energy at all, so the total work done on the block is equal to 0. Part B. We're now asked to calculate the work done by the rope on the block. So the rope is doing work on the block, it's just that there's other forces such as friction, which the block is doing work to overcome. Hence the total work can be 0. Okay, so to work out the work done by the force F, work is equal to the dot product of the force and the distance covered. So to do the dot product, we only consider the component of the force acting parallel to the distance it's moving. So that's this part here. So this is equal to 7.68 cos 15 times the distance it's moved, 4.06. Doing that on the calculator, we end up with 30.12 joules, which we should just give to 3 significant figures, as all these numbers are to 3 significant figures. So let's write that as 30.1 joules. Okay, part C. The work done by friction on the block. Well, let's consider all the forces acting on the block. We've got the weight force acting downwards and the reaction force opposing that. We've got the friction force, which will oppose the movement of the block. And we've got the force F acting on the block. So those are all the forces acting. So if the total change in energy, or the total work done, 0, then the work done by friction must be the same magnitude as this work, but have the opposite sign. So work done by friction is equal to minus 30.1 joules. Okay, part D. We're now asked to find mu k. Okay, so here's our normal force. I simplified it overly much before when I said this was just due to the mg. It's also due to the component of this force F here. So to find mu k, we know that the frictional force is equal to mu k n, and we know that the work done by the friction dot d is equal to minus 30.1, and these are parallel, so the frictional force times D is equal to minus 30.1. So our total frictional force is equal to 7.41 newtons. Okay, so we have this number and we can work out N. So let's work out our normal force. To work out the normal force, let's draw a diagram of all the components of these forces which are perpendicular to the plane. So we've got mg acting downwards. We've got this force here, which is F sine theta, acting upwards. And we know that all these add to 0 as the block is not accelerating upwards or downwards. So the normal force will add in here. And so the normal force has magnitude mg minus F sine theta. Okay, let's just substitute in the numbers. So this is 3.57 times 9.8 minus 7.68 sine 15. Doing that on the calculator, we end up with 32.998 newtons. And so this tells us that 7.41 is equal to mu k times 32.998, and so mu k is equal to 7.41 over 32.998, which on the calculator is 0.225. Now this is in newtons, this is in newtons, so there's no units for this, which is what we'd expect for the coefficient of kinetic friction. This is problem 8 for 1121 or problem 10 for 1131. In this problem, we're given the expression for the potential energy of a particle. It's given by A over x to the 12 minus B over x to the 6, where A and B are constants. In part A of the question, we're asked to calculate the force between the atoms that experience such a potential. So we need to use the equation F is equal to minus du dx. So to make this easier to differentiate, let's write this as ax to the minus 12 minus bx to the minus 6. Okay, so this is minus, that's just this minus sign, and now we're going to differentiate it. So this is minus 12ax to the minus 13 plus 6bx to the minus 7. So we can write this as 12a over x to the 13 minus 6b over x to the 7. We're then asked to plot that along the x-axis. So here's our x-axis. Now when x is 0, this is infinite, but this is bigger. So this is going to have an asymptote up here. Let's work out when it crosses the f equals 0 line. So we have 12a over x to the 13 is equal to 6b x to the 7, which tells us x to the 6 is equal to 12a over 6b, which is equal to 2a on b. So x is equal to 2a on b to the minus 6. So that value, if that's there, this goes here. Okay, now as x goes to infinity, this is going to approach 0, this is going to approach 0 as well. This one will always be slightly bigger, so it'll approach 0 in this way. So this suggests that we're going to have a shape like this, which is actually a very similar shape to the shape for ux. And now part B asks us find the equilibrium separation between the atoms. Well, it's at equilibrium separation when the force is 0. We've actually already solved 0 is equal to 12a over x to the 13 minus 6b b over x to the 7 here to find out where it crossed this x-intercept. So the equilibrium separation is equal to 2a on b to the minus 6. This is problem 9 for 1121 or problem 11 for 1131. In this problem we have a spring. Here's a fixed end, here's our spring, and we can apply a force to extend the spring. This spring doesn't obey Hooke's law, which remember is F equals minus kx. Instead it obeys the law F is equal to 52.8x plus 38.4x cubed. Part A of this question asks, compute the total work that we need to stretch the spring from 0.500 meters to 1.00 meters. Okay, so the change in potential energy or the work done is equal to the integral of f dot dx, and dx, we're changing our x from 0.500 to 1.00. So substituting in, we've got 52.8x plus 38.4x cubed dx, 0.500, 1.00 is the limits. And so integrating this, we end up with 52.8 on 2x squared plus 38.4 on 4x to the 4, and our limits. So substituting our limits into this equation, we end up with, when we put 1 in here, we get 26.4, plus putting 1 in here, we get 9.6, putting 0.5 into here, remember our minus sign, we get minus 6.6, and then putting 0.5 into here, again with a minus sign, we've got minus 0.6. So putting all that into the calculator, we get 28.8 joules. So that's the work that needs to be done on the spring to extend it from here to here. Next, part B. Okay, we now have one end of the spring fixed. We extend the spring out to the 1 meter mark, and we attach a 2.17 kilogram mass to it. And then we're asked when the mass, this is at 1.00 meters, when the mass reaches 0.500 meters, what's its speed? Okay, well the work that we put into stretching this spring, the spring then does as it contracts again. So we have that the change in energy of the block is equal to 28.8 joules because the block is attached to the spring, so the spring is doing the work on the block now. And so that change in energy, there's no potential involved here, there's no gravitational potential, we're not lifting it up, and there's no other potential either, so this energy is in the form of kinetic energy. So this is equal to a half mv squared for the mass, which is a half times 2.17 times v squared. Okay, so solving for v squared, which is equal to 28.8, we have v is equal to multiply by 2, divide by 2.17 and take the square root. We get v is equal to 5.15 meters per second. And velocity also needs a direction, so obviously this mass is going to be moving in this direction, so back towards the fixed end. Now part C says, is the force exerted by the spring conservative or non-conservative? What's a conservative force? Because all the work we put into the spring comes back as a gain in kinetic energy by the block. So we could repeat this again and again and again without losing energy. So that is a conservative force. Okay, we're doing problem 10 for 1121 or 12 for 1131. In this problem, we have two masses. We have mass A, which is connected to mass B with a string over a pulley. Mass A is 6.0 kilograms. Mass B is 4.0 kilograms. We've got friction on this surface, and mu k is given by 0.30. And we're going to have tension in this string. So part A asks us to find the acceleration and the tension in the spring by using Newton's second law or otherwise. So we'll use Newton's second law, which tells us that the acceleration of the masses is equal to the resultant force on the masses. So let's write an equation for mass A to start with. Mass A times the acceleration is equal to, now the largest force acting on mass A is the tension force, which is pulling it in this direction. The other force acting on mass A is the friction, which is going to oppose the direction of movement. So this tension force is causing it to move this way. So this is going to be minus mu k. Now the friction force is given by mu k times the normal force, which in this case will just be mag. So let's call that equation 1. Now we can write an expression for the acceleration of this second mass. So in this case we've got mb times the acceleration is equal to, now the largest force acting on mass B is going to be the gravitational weight force. So we've got mbg, and then the tension is acting upwards to oppose that. So this is equation number 2. Now to find acceleration, what we can do is just simply add these two equations. So we've got the acceleration ma plus mb. When we add them, the t's will cancel out because one's positive and one's negative. So we've got mbg minus mu k mag, and so a is equal to g mb minus mu k ma over ma plus mb. We need to substitute in our values, so 9.8 times 4 minus 0.30 times 6 over 4 plus 6. Doing that on the calculator, we end up with 2.156 meters per second. So we write this as 2.2 meters per second. Okay, now we're all in this part of the question. We're also asked to find the tension. So equation 2 is slightly simpler, a few less terms. So let's substitute into that. So the tension is equal to mbg minus a, just rearranging this equation, which is equal to 4.0 times 9.8 minus 2.156. We use all the significant figures in the working, and this ends up giving us 30.57 newtons, which is equal to 31 newtons. If you'd used the 2.2, you actually would have ended up with 30 rather than the 31. So this is an example of a question where it's important to continue using all the significant figures even though you present the final answer to only 2. Okay, so next, part B, we're asked to calculate the kinetic energy of the system after the two blocks have moved 1.5 meters. Now, an important observation is that because they're tied by a taut string, they will have the same velocity when they've moved that distance. So we can solve the kinematic equations for one of these masses to get its velocity, and that is also the velocity of the other mass. Okay, so let's solve the equation v squared is equal to v naught squared plus 2ax. Let's solve it for mass A. Doesn't matter which one we do because they both have the same acceleration. So they both start from rest, so this is 0 plus 2 times the acceleration, which is 2.156, times the distance that they travel, which is 1.5 meters. Okay, doing this on the calculator, we end up with 6.468. Now we don't actually need to solve for V because we're going to be doing kinetic energy. And the kinetic energy is equal to half mv squared. So substituting in, we have a half the mass of the system. Both these blocks are travelling at the same speed. So 4.0 plus 6.0 times 6.468. Doing that on the calculator, we end up with 32.34, which is equal to 32 joules. Okay, finally part C. Now we need to work out how much energy is developed as friction between mass A and the surface. We have mu K is equal to 0.30. Okay, so the work done by the frictional force is equal to F dot dx for this frictional force. It's starting from its initial position, it's going to 1.5 meters. So from 0 to 1.5, the frictional force is equal to mu K times the normal force, so mg dx. Substituting in, these are all constants, so we end up with mu K mgx from 0 to 1.5. Now all we need to do is substitute in the values. When we put in 0, it won't count. So we've got 0.30 times 6.0 times 9.8 times 1.5. Doing that on the calculator, we end up with 26 joules. So the frictional force does 26 joules of work, and that work gets converted to the heat energy. This is problem 11 for 1121 or 13 for 1131. In this problem, we have an inclined plane. Inclined is an angle of 30 degrees with a spring on it. We compress the spring with a block. The block has a mass of 2.0 kilograms. And the spring is compressed 20 centimeters. And we're asked how far along the plane will this block travel? Well, to answer this question, we need to consider the energy involved. The energy which is done as work to compress this spring will be, and then stored as potential energy in the spring, will be converted into kinetic energy and then gravitational potential energy in this block. So we can use that to work out how high the block has actually travelled. So the energy stored in the spring is given by a half kx squared. The spring constant for this spring, we're told in the question, is equal to 1,960 newtons per metre, and it's compressed 20 centimetres. So doing this on the calculator, we end up with 39.2 joules of energy stored in the spring. Spring's then released, pushing the block up the slope. So when the block gets to its highest point on the slope, all that energy has been converted from kinetic energy into gravitational potential energy. And so the 39.2 joules has become gravitational potential energy. So the height that it will rise to is 39.2 over the mass of the block, which is 2.0, times the g, which is 9.8. Solving that on the calculator, we get 2.0. So it's risen 2 meters in height. This isn't what we're asked for in the question. What we're asked for is how far along this plane will it go. So if it goes a distance L, this is 30 degrees, and it's risen a height of 2.0 meters, we need to find L. Well, we know that 2.0 is equal to L sine 30. So L is equal to 2.0 over sine 30. Sine 30 is just a half, so this is equal to 4.0 meters. So it travels 4.0 meters up the plane. This is problem 14, which is for 1131 only. In this case, we have a ramp with a flat bit with some friction down the bottom here. So we have a block which is initially released from a height h, and then there's a section with friction here which has length h and a coefficient of kinetic friction equal to 0.15. And in part A of the question, we're asked how high does the block rise on this side of the track after it's passed this place with the friction. So what happens as it passes the place with friction is that the block has to do work to overcome the friction, and so that work causes it to lose some energy, and so some of the gravitational potential energy here, which is converted into kinetic energy, is lost, so it has less gravitational potential energy here. So let's write down some equations to describe that. Well, the work is equal to the integral of f dot dx, which is just equal to fx in this case, and the force is given by mu k mg, the coefficient of friction, times the normal force, times the distance x, which in this case is h. This rough spot has a length h. Okay, so at this highest point, all the energy is as gravitational potential energy. So U initial is equal to mgh, and what we want to find out is the final energy here. So UF is equal to the initial energy minus the work that the block has to do to overcome this friction. So this is equal to mgh minus mu k mgh, and the final energy, if we call this height h dash, it will all be in the form of gravitational potential energy, so we can write this as mgh dash, where h dash is the new height. Okay, so now we can solve this to find out h dash. Mg occurs in every term, so we can cancel those out. So h dash is equal to h minus mu k h, which is equal to h outside of 1 minus mu k. Substituting in the value for mu k, we have 1 minus 0.15. And so this is 0.85 h. Okay, so it's losing 0.15 h each time. Okay, now part B asks how many times will the block pass point A, which is here. It's important where on the track A is, in either direction. Okay, so we can get an approximate answer by doing number of times is approximately equal to 1 divided by how much height it loses each time, what percentage of the height it loses. So this is equal to 6.67. So now we need to think about this number, because it's not going to pass point A 6.67 times. It will pass A an integer number of times. So it'll pass it once and it will have a height 0.85 h, and then again and it will have a height 0.70 h, and again and again, and we find that it actually comes to a stop here around about 2/3 of the way across after passing point A 7 times. So it's 7 times. If point A was here on the track, or if this is point B, it will pass point B only 6 times. So that's why this isn't the answer. We have to come up with the integer, and that will depend where on the track the point A is. Okay, problem 15, which is 1131 only. In this problem, we have a circle. It's got a radius r, and we consider a mass with mass m, and the mass slips along the surface of this circle. There's no friction, so it's not losing energy that way. And first of all, we're asked to calculate the change in potential energy with angle. So let's, the change in potential energy is equal to the final potential energy minus the initial potential energy. So the initial spot is here, and it has a height r. Here, let's calculate the height here. This is theta. So the height here is r cos theta. And so we've got the change in potential energy, U is equal to mgh. We'll just need to substitute in our appropriate h's, is mg. Now the height at the final spot is r cos theta. The height at the initial spot is r. So this will give us the change in the potential energy. So we can write this as minus mgr 1 minus cos theta. Okay, part B says the kinetic energy is a function of angle. We're told there's no friction, so there's no forces doing work, and so the gravitational potential energy that's lost is gained as kinetic energy. So the gain in kinetic energy is equal to mgr 1 minus cos theta. Okay, part C says find the radial and tangential accelerations as a function of angle. Okay, so let's start with the radial acceleration. Our equations for circular motion, which this is, it's following a circle, tell us that the radial acceleration is equal to v squared on r. And now the kinetic energy is equal to a half mv squared. So the change in kinetic energy is equal to 1/2 mv final squared minus 1/2 mv initial squared. Now we're told that it starts from rest, so this term's 0 because v initial is 0, and that is equal to mgr 1 minus cos theta, where v final is this v which we're interested in here. And so v squared is equal to, our m's will cancel out and we'll have 2gr 1 minus cos theta. And so our radial acceleration, we substitute this in for v squared, and so we're dividing this by r, we end up with 2g 1 minus cos theta. Okay, now tangential acceleration is caused by the gravity g. So we've got the acceleration acting downwards like this. We can break this into a tangential and a radial component. These are at 90 degrees to each other. Here's our radial component, here's our tangential component. And then considering the geometry up here, this here is 90 degrees. So the angle that the vertical makes with the tangent is equal to 90 minus theta, so this will be theta down here. So the tangential acceleration will be given by g sine theta. So AT is equal to g sine theta. Okay, part D asks the angle at which the mass flies off the sphere. Well, the mass will fly off the sphere when the radial acceleration due to gravity is greater than the radial acceleration which is keeping it on the sphere, this one here. So the radial acceleration due to gravity, we can see here, is equal to g cos theta. When this and this are equal to each other, the acceleration due to gravity will be larger than the radial acceleration, and so it will fly off the sphere. So we can write g cos theta is equal to 2g 1 minus cos theta. So this is equal to 2g minus 2g cos theta. So moving this term over to this side, we end up with 3g cos theta is equal to 2g. Cancelling the g's gives us cos theta is equal to 2/3, giving us theta is equal to the inverse cos of 2/3, and that's our answer. Problem 16. This is for 1131 only. Okay, in this problem we have a table. We have a spring hanging off it with some spring on the table. The spring has mass m and length L. There's a length x hanging down and there's a force F which is causing this spring to slide very slowly onto the table. The slowly implies that this is constantly at equilibrium, which means that the net force is equal to 0. Okay, part A of the question asks us, calculate the magnitude of the applied force when the length x of chain remains hanging. Okay, like we said, it's at equilibrium, so F net is equal to 0. So the applied force must be equal to the weight force. Okay, so to work out the weight force, we need to know the mass of spring which is hanging. So the density per unit length is m divided by L, and the length hanging is x. So this is the mass of spring hanging, and then to get the weight force, we have G. So F is equal to m on L x G. Okay, part B says sketch F as a function of x. This is easy. Here's F, here's x. When F's 0, x is 0, so it starts at the origin, and it's a nice straight line with gradient equal to m over Lg. Okay, part C. Calculate the total work needed to pull all of the rope onto the table. Okay, so initially we have the rope hanging down like that. Finally, it's like this. So the length on the table is initially 0. Finally, it's equal to L. Here x is equal to L, and here x is equal to 0. So you can see there's a relationship between the length on the table S and the length hanging x. We can write S is equal to L minus x. And so you'll see later why this is useful, but we can write ds dx is equal to minus 1. Now the work done to pull the rope onto the table is equal to F dot ds. Initially the length on the table is 0, finally it's L. Now what we want to do is change variables. We don't really want to consider the length on the table, we want to consider the length hanging, as that's what we've got all the formulas for. Okay, so to do that we change from ds to dx, and we also need to change our limits here. So we have minus dx to replace this ds. When s is 0, x is L. When s is L, x is 0. And now we can substitute in for this f from up here. We can put the m on Lg out the front because they're constants, and we have x dx. So this is equal to minus m on Lg, x squared on 2 from 0 to L. Substituting in, we have minus m on Lg minus L squared on 2. Okay, the negatives cancel each other out. One of these L's will cancel, and we end up with mLg on 2 as the work done to pull that spring onto the table. Okay, finally part D says calculate the change in potential energy of the rope if initially it's all hanging. So the change in potential energy is equal to the final energy minus the initial energy. And so the change in potential energy is also equal to the work done, because that work done is all gained as potential energy. It's pulled very slowly, so it's not gaining any kinetic energy, and so this is equal to mLg on 2. Okay, and the past exam question. In this question we have a track with the loop at the end. The radius of the loop is given by capital R, and we have a little toy car here which starts at a height h. Most of the mass of the car is concentrated here. The wheels have very little mass, and there's no friction. We can neglect air resistance. Part 1 asks us what is the minimum height that we can release the car from for it to go around this loop without losing contact. Well, the place where it's most likely to lose contact is the maximum height here on the loop, in which case it has acceleration g downwards, and we need the centripetal acceleration to be equal to that g for it to maintain contact. So the limiting case will be when v squared on r is equal to g. Okay, so we can use this to work out what the height is going to be by considering the energy. Okay, there's no friction, so we can ignore any work done. There shouldn't be work done in this case. So if we call this the initial place and this the final place, then the initial potential energy plus the initial kinetic energy should equal the final potential energy plus the final kinetic energy. So the initial potential energy is mgh. it starts from rest, so the initial kinetic energy is 0. The final gravitational energy is mg. Now this height is, the radius is r, but it's 2 radii up above the ground, so this is 2r plus a half mv squared. Okay, so we can solve this to work out what v squared is. Let's cancel all the m's, and then we have a half v squared is equal to g h minus 2r, and so v squared is equal to 2g h minus 2r. Okay, so now we've got v squared, and we can substitute that in here. So we have g is equal to 2g h minus 2r over r. Cancelling out the g's. We need to solve this for h. So we have r is equal to 2h minus 4r, and so 2h is equal to 5r, and so h is equal to 5 over 2r. Okay, part 2. Does this depend on the mass of the car? No, it doesn't, because if the car is heavier, it has more potential energy to start with, and that gets converted into the final potential energy and kinetic energy. So m drops out as a factor, and so it's independent of the mass of the car. And then part 3. If a solid ball were released from this height in 1, would it maintain contact throughout the trip? And explain your answer. Well, a ball also gains rotational kinetic energy. This cart doesn't rotate as it slips down the track, so all its potential energy is converted into translational kinetic energy. If this was a ball, some of the kinetic energy would also be converted into rotational kinetic energy, and so it wouldn't all be translational kinetic energy. So the velocity up here would be lower, and so it would not have enough velocity to maintain contact with the track.